Sure. I just want to say good afternoon to everyone. I am Carrie Fagan, the director of Northwestern OLLI. Welcome to this unique opportunity for us to come together in a partnership event between all the Illinois OLLI programs, Northwestern and Bradley and University of Illinois. As a new director, I will tell you, I'm really thankful for the opportunity to work with Chris and Michelle, who are the other OLLI directors that you see on your Zoom screen. We had a lot of fun planning this event. And it's been a great partnership because all three of us care deeply about OLLI and about providing our members with the best possible OLLI experience. And I think you're going to see that in our discussion today. So I'll remind everyone of some logistics. This is a webinar, meaning you can see and hear us, but we cannot see and hear you. However, you will have the opportunity to engage with our presenter during the latter part of our event by entering your questions in the Q&A feature, which you'll find on your Zoom toolbar at the bottom of your screen. So that's all I have logistics wise. Michelle, do you want to jump in?
Sure, thanks, Carrie. On behalf of the Osher Lifelong Learning Institutes at Bradley, Northwestern, and U of I, along with the National Resource Center for Osher Institutes, I want to personally welcome everybody for coming to today's event. Like Carrie said, I'm Michelle Riggio, Director of OLLI at Bradley, joined by my colleague directors, Carrie Fagan from Northwestern and Chris Cantanzarite from U of I. I practiced that one, Chris.
For
the past few summers, the three OLLIs in Illinois have gathered at an outdoor venue to enjoy a meal, a presentation, and a performance by the Chicago Symphony Orchestra. A beautiful night under the stars just wasn't in the cards for 2020. So instead, we're gathering virtually today with almost 400 OLLI members from across the country to do what we do best, and that's learn as a community. And it's really an exciting time for all of our OLLIs as we continue to grow and evolve to find ways to bring you interesting learning opportunities. And as we enter 2021, we'll continue to find ways to plan events like today's until we can finally get together in person. And I know each and every one of us can't wait for that day to come. So welcome. We're very, very glad you're here, and we all hope that you enjoy today's presentation.
Thanks so much, Michelle and Kari, and thank you most of all to today's distinguished speaker, Professor Nigel Goldenfeld, who I'll tell you a little bit about in a minute. This Tale of Three Cities started in 2017 when we had a conference presentation that focused on the unique and uniquely local characteristics of the OLLIs in the state of Illinois. And today we gather members from all of our institutes for another uniquely Illinois story, and one that has national and global significance as well. The modeling that's being done by Professor Goldenfeld and his colleagues has produced one of the most comprehensive testing mechanisms in the country. And the work that he's done with the Illinois Department of Public Health has helped to determine the mitigation strategies that have affected us all over the past several months. So it is my great pleasure and honor to welcome Professor Goldenfeld today and to introduce him to you. Nigel Goldenfeld holds a Swanlund Endowed Chair and is a Center for Advanced Study Professor of Physics at the University of Illinois at Urbana-Champaign. He is the director of the NASA Astrobiology Institute for Universal Biology and leads the Biocomplexity Group at the university's Institute for Genomic Biology. He's the recipient of numerous prestigious honors and awards, and his publications number in the hundreds. He is a fellow of the American Physical Society, a fellow of the American Academy of Arts and Sciences, and a member of the U.S. National Academy of Sciences. His presentation today is titled, How to Stop COVID-19 Using Mathematics. Just a reminder, type your questions if they occur to you throughout the presentation in the Q&A box. And at the end of the lecture, we'll share them with Professor Goldenfeld and get some answers. Thank you all. Thank you, Nigel. Have a wonderful lecture. Thanks.
Well, good afternoon, and thank you so much, all of you, for inviting me to give this lecture. I've lectured several times at OLLI, and I've always found it an exciting experience. And I know that I'm going to get great, wonderful incisive questions at the end, and I'm looking forward to answering those for you in due course. So what I want to tell you about is a strange story, one that is perhaps counterintuitive. People wonder, shouldn't you be stopping a disease by medicine and things like that? And of course, the answer is yes, you should. But mathematics plays a role in this. And so what I'd like to do is give you some flavor of what it can help us understand and how it can help us to make things better. So let me share my slides, and then we will get started. So give me 1 second here. All right, and could I ask one of the hosts, Michelle or Carrie or Chris, to please be on video, because when I give the talks, I find it very difficult to just talk at a blank screen. So it's nice to have a little human being up there in the corner. I always try to put myself on self-hide my own image, but at least I get to see people, and so I know that everybody's still there as well. All right. Okay, and then the last thing before we get started is let me get a laser pointer. So bingo, now we have a laser pointer. All right then. So I'm going to tell you about a story that started about 8 or 9 months ago, an adventure that I shared with my colleague Sergei Maslov, who's a professor in bioengineering and physics and has the office next door to me at the Institute for Genomic Biology. And the first half of the talk will be about work that we did advising the state of Illinois at an early stage during the COVID epidemic. And then then for the second half, I'm going to talk about what we've been doing at the University of Illinois in keeping our campus open despite a raging epidemic, and how we did that, and how mathematics helped us to do that. And that involved the following individuals: Professor Ahmed Albana, who's in civil engineering and who I've worked closely with on that, and a few very talented graduate students, Zach Weiner, who in his day job is a cosmologist, Tong Wang, who in his day job works in genomic biology and the microbiome and things like that, microbiology, genomics, metagenomics. George Wong, whose images you may have seen in the newspapers, because he works on the Event Horizon Telescope that was responsible for the first images of the event horizon of a black hole. And he worked very extensively on that. Hantao Zhang, who was an undergraduate who did a summer project with us. Alexei Tkachenko, who's a close collaborator of Sergei's and mine and works at Brookhaven National Laboratory. And lastly, a graduate student at Stanford University, Zhiru Liu, who used to be an undergraduate in my group a year or so ago, and now as a graduate student, and worked with me on topics to do with evolutionary biology. So that's who those are the credits. So now let's have some fun, and the best way to have fun at this time of the year when it's dark and you can't go outside and it's cold is to be inside and play chess. So here is a wonderful chess game that you can see being played on the board, and this isn't in fact any chess game. I'm going to skip 19 chess moves to the end. This is the closing position, and some of you, if you're chess aficionados, may recognize this game. This is the final position in a game by Stefan Levitsky and Frank Marshall in 1912. And in this position that you can see on the board, and let me just put it there just so that you can take a screenshot and look at it. This position was one where white resigned, even though you might think that white could go and take the black queen and win the game. And in fact, this is just a beautiful chess game. It's a fantastic ending where if you do the obvious thing, you find that you lose. And in fact, even if you do all the things that aren't obvious, you still lose. It's absolutely amazing. And at the end of this game, according to legend, the spectators showered the board with gold coins to show their appreciation. So this is just an example of the beauty and wonders of chess. Now, there's another legend about chess, and that legend goes as follows. Somebody, a sage, presumably invented chess, and a king, I believe the story is that it's a king in India, but I don't know if that's true, said that as a reward, I'll give you anything that you want. And so the story goes that the inventor said, well, I'd like the following. On day one, I'd like you to give me a grain of rice and put it on the first square of the chessboard. On day two, I'd like you to give me 2 grains of rice for the second square. And on day 3, I'd like you to give twice that number. And on day 4, I'd like you to give twice that number, and so on and so forth. And so on day 4, you would have 2 times 2 times 2 grains of rice. Day 5, 2 times 2 times 2 times 2 grains of rice, and so on and so forth. Now the chessboard has 64 squares. So the question is, how many grains of rice would there be on day 64 when the reward would finish? So we can work that out quite easily, because on day 5, the inventor has got 1 grain of rice for the first day, plus 2 grains of rice for the second day, plus 4 grains of rice for day 3, plus 8 grains of rice for day 4, and so on. And so by day 5, the inventor would have had 31 grains of rice. Okay. If you think that's an interesting number, you're right. That number is 2 to the 5th, 2 times 2 times 2 times 2 times 2, 5 times, minus 1. And so if you ask what would you get on day number n, the answer would be 2 to the n minus 1 grains of rice. Okay, so there's a little bit of simple mathematics there, nothing fantastic. But let's keep going and seeing what happens as we go further on and beyond day number 5. So by day 15, the inventor of the game of chess would have about 32,000 grains of rice, which is about a pound of rice, and that's worth a few dollars. And you might say, this is a kind of tiresome story. What is in it for the inventor? But by day 20, you find that the inventor has about 1 million grains of rice, and that may be worth about $50. By day 36, the inventor has several $1 million worth of rice, and by around day 50, the inventor has more rice than is produced on the entire planet in a year. So you can see that this is actually, the inventor was actually quite wise. This seemingly humble gift would actually make them fabulously wealthy. And so this is what you can see shown here in this graph. So here is the calendar day, and here is the number of grains of rice, and therefore how wealthy the inventor is. And you can see that it starts off extremely slowly, by hardly any money at all by day 15 or day 20 or whatever. But at the end, it really grows surprisingly rapidly, and at the end, you have an unfathomed wealth. So this kind of graph is called an exponential graph, and any curve that follows this exponential law will start off slow and then will rise very rapidly at the end. So let's see some other examples of that. So one example is nuclear fission. So you've heard of uranium, particularly the isotope uranium-235. So that's an unstable atom, and what that means is that if a neutron collides with that atom, it will cause it to split. When it splits, it produces 2 or 3 other neutrons. So you have an atom, and a neutron from who knows where crashes into it, and it splits the atom and produces 2 or 3 other atoms. And so those neutrons will then go and hit other atoms, and those will produce more and more neutrons as well. So on average, each atom that splits produces about 2.4 neutrons. Just turns out to be that way. So these neutrons collide with other neutrons, with other atoms rather, to produce more neutrons. And so what you get is a chain reaction shown here. So here I've shown you one atom will then produce enough neutrons to split 2 other atoms, and those will produce 2 neutrons to split 2 other atoms, and so on. And if you ask how many atoms have been split and how many neutrons there are, you can see these numbers 1, 2, 4, 8. Again, the same numbers that I showed you in the grain of rice. And this is called an uncontrolled chain reaction. And if you've got enough atoms in your sample, then this process will continue many times, and it will generate not just neutrons, but energy. And this is in fact how a nuclear bomb works. And you might ask, how do I know how much stuff I need to make a nuclear bomb? And so you have to work out how many of these fission events do you need in order to produce an explosive amount of energy. And one can do that calculation. So you can also control nuclear reactions, and the way you can control them is you put in materials that absorb some of the neutrons. So if you have some other material there that absorbs the neutrons, the reaction doesn't grow, but just keeps going roughly, let me go back, producing producing 1 neutron that then splits another atom in each splitting. So by absorbing the extra neutrons, the number of neutrons doesn't grow as it did in the previous slide, 1, 2, 4, and 8, and so on, but it just stays the same, 1, 1, 1, 1. And so this is a chain reaction that is critical. It just sits there and it just keeps producing neutrons, keeps producing energy, and so that's how you make a nuclear power station, roughly speaking. So if you've not got enough atoms, or something absorbs the neutrons, the reaction doesn't grow, it just keeps generating energy. And so that's a nuclear reactor. So that's a critical chain reaction. So COVID-19 is a biological atomic bomb. And this is why. One person can get COVID, and one person can infect 2 other people. And then those 2 other people can infect 2 other people, and those 2 other people can infect 2 other people, and so on and so forth. This is exactly the same picture I showed you before for the chain reaction. But now what's happening here, these arrows indicate infections rather than neutrons splitting atoms. And so you have an uncontrolled chain reaction. And that's what an epidemic is. The number of infected people just keeps on growing. And it keeps growing exponentially in this way that I showed you before. And what we say is this: there's a number that you've probably heard about on the news called the R number, or the reproduction number. So in this example here, each person infects 2 other people. And so we say that the reproduction number of the epidemic is R equals 2. Okay, so that's why an epidemic is so dangerous. It's an a biological atomic bomb. Let's just talk a little bit about why it's such a big health hazard. And here I'm going to show you a slide produced by one of my colleagues at the university, Jessica Brinkworth. So this is a slide that she made for a joint presentation that we were giving early on in the epidemic, and I'm going to draw on that. So the question is, why are we so concerned about COVID-19? So here, and let me just backtrack a second. Here I'm showing you several diseases. So here's COVID, of course. This is regular influenza. This is SARS, an epidemic that happened about 15 years or so ago. This is MERS, an epidemic that happened about 10 years ago. And I want to just contrast these things. So if you look at the reproduction number, this chain reaction number that I just showed you, what you can see is that it's about 1.3 for the flu virus, but it's about 2 to maybe even as high as 6 in some cases for COVID. So you infect far more people. So it's a much more transmissible disease than just the flu. Then the question is, how many people will get infected and have such a bad reaction that they end up in hospital? And the answer is, it's about 10 times more likely that you're going to end up in hospital with COVID than you would with the regular flu. And then you might ask, well, how many people will be killed by COVID? Now, at the time I wrote this slide, the answer was about 62,000 people had died at that time. And in a typical year, flu will kill maybe 10 to 61,000 people in the US. So at that time, this was somewhere around May, if I remember correctly, COVID had killed more people in the US in just 2 months than flu does in the worst year. So those are the reasons why we take this very seriously. Now, these data were from May the 5th here. I was wise enough to remind myself when that is. So what happened? Well, 2 weeks later, we were above 94,000 deaths. And since then, the number of deaths has grown very rapidly. And today, as you know, we're well above 200,000. So it's a very, very, very deadly disease. Okay, so now I want to tell you a little bit about my history and my background and the background of my collaborator, Sergei Maslov. So you might ask, why are you guys talking about COVID? Because you're not qualified to do that. You're not epidemiologists, you're not medical doctors, and you're absolutely right, we're not. We are physicists, and I'd say that during the last 20 years or so, physics has become a very interdisciplinary field, even more so than it had been before. Now, my background is in what's called statistical physics. And the idea there is you use statistical reasoning to solve problems in physics. And some examples of those kind of problems are this. Suppose I've got atomic physics. There I might be looking at what happens to one particular atom and how it behaves and so on and so forth. If I'm dealing with a huge number of atoms, or the number of atoms that might be, in a pound of iron or something like that, sitting on your desk. Now you've got about 10 to the 23 atoms. It's a huge number, and the number, when the number is so large, matter behaves differently than when the number is small. There's a famous article called "More is Different." And in fact, we know that when you have a large number of atoms, you can self-organize into phases like the solid phase, or the liquid phase, or a magnetic phase, or something exotic like a superconductor, or a quark gluon plasma, or any of these other things. So huge numbers of atoms behave differently than single atoms, and that's what I work on. Now, that's my day job. About 20 years or so ago, I started applying these kinds of physics techniques to studying not matter, but to studying living matter, to studying ecosystems, to studying evolution, to studying populations of viruses and bacteria, genes, and even honeybees. In fact, just yesterday, I had a paper published with Jean Robinson, my colleague here at the Institute for Genomic Biology, studying the collective behavior of honeybees in a hive. And so I know that even the newspapers in England reported on that work, so you may have seen that as well in the news. So we study these same physics methods applied to living systems. Now, this mathematical modeling that we use in ecology is also the foundation for mathematical modeling in epidemiology. And so it was very easy for us to pivot from our regular research in biology to studying epidemics. Now, if you cast your mind back to February and March, you may remember that it was very difficult to get a COVID test in Illinois and indeed in America. And the only way that one could tell how many people were actually infected was through mathematics. And in fact, even in March, in the middle of March, there were in Illinois maybe only about 100 cases of COVID that were known. We could already tell that there were a lot of cases in Illinois that had not been discovered and not been disclosed through testing. And we could also predict how one should prevent the growth of the epidemic, and in fact predicts the effect of a preemptive stay-at-home order. Now, why I say preemptive stay-at-home order? Because as you know, in Illinois, we had a stay-at-home order that started on March the 21st, which I'll get to in just a minute. And we did that before the epidemic had got very far advanced. Those of you who might have been in New York State or might remember, in New York, there was absolutely a disaster happening there. The hospitals overflowed, many cases and deaths happened. But that was avoided in Illinois. And so I want to tell you a little bit about that. So here is a graph from data that we took early in March of this year. So what I'm showing you here is the number of confirmed cases of COVID in Illinois, and these are the dates, March the 11th, 12th, 13th, 14th, 15th, and so on and so forth. And what's plotted here is a logarithmic scale. That's a special type of way of transforming the axis, so that anything that is growing exponentially will just be a straight line on that graph. And you can see here that here are the data, and the dashed line is the exponential fit, the mathematical function that described that slow to start and then rapid to rise graph that we saw in nuclear reactors, that we saw in the grains of rice on the chessboard problem. That mathematical function, you can see that these number of cases is growing following that mathematical law. And there were about 20 or so cases on March the 11th. A week later, you had 100, and it was growing exponentially from then on. So here you can see exactly how that transpired. So this now is from a wonderful website by one of my colleagues at the University of Illinois, 91divock.com. This is the same logarithmic scale. This is what I just showed you down here in the corner. And now when we go further out in time, you can see the number of cases is growing exponentially, and then eventually started to flatten the curve. And so by May the 20th or so, we had more than 100,000 cases just in Illinois. That's how rapidly this was growing. Now, let's think about what this exponential curve means for hospitalization. So let's suppose now that we're plotting the same curve that I showed you for the grains of rice, but now we're going to infer, we're going to say that the variable that we're plotting is the number of severe cases rather than the number of grains of rice. It's the same function, and this red line that I've drawn here is meant to represent the capacity of the ICUs in the state of Illinois. So you work out how many beds you have that you can give over to COVID patients. It's some number, and that's that number over here. And so what this curve would say is that the ICUs would start to fill up very slowly, but then they would start to, the number of cases would start to rise very rapidly, and towards the end would rise very quickly and overflow the ICU capacity. So let's just translate that into a narrative. Let's suppose that the doubling time for COVID was about 2.5 days. And that actually is indeed what was happening. Back in March, the epidemic was doubling every 2.5 days. In Italy, it doubled for 2.5 days for nearly a month. And that also caused an absolute disaster. So let's think about what this means, the inexorable mathematics of exponential functions. So the doubling time is 2.5 days. So let's suppose it's Sunday. And you look around in your ICU in your hospital, you're the director of the ICU in some hospital, you look around and you see the ICU is half empty. So you say, great, we're in really good shape. We've got plenty of beds here. You know, we can deal with any emergency that's going to happen. Everything is just fine. But it doubles every 2.5 days and you're half empty. So that means that by Wednesday, your ICU is full. And by Saturday, your ICU is overflowing and the doctors are treating sick patients in the car park because there's no room in the hospital. That's the meaning of this rapid rise here. And that's why it is so dangerous to have this biological atomic bomb, to have this exponential growth, because it sneaks up on you. You think everything is fine, and then within a couple of doubling times, 2.5 days in the case of COVID, you suddenly run out of the ICU. So that's why it's a big problem. So Sergei Maslov and I took these data. We figured out how to model the epidemic, and what we asked ourselves was the following question. It became clear that throughout the world, the only way to deal with the epidemic at that time was to do lockdowns, to do stay-at-home orders. So we asked the following question. Let's suppose that we were to do a shutdown, a stay-at-home order, and we're going to assume that the stay-at-home order can be implemented at 2 different times. So one time you could do it by April the 1st, the other time you could do it would be April the 20th. So we'll call this scenario delayed mitigation, and the just-in-time scenario the one where you implement a stay-at-home order very quickly. So when you do the calculation and you calculate how many ICU beds are needed in Chicago, which was the only place that we had data for, we found 2 possible curves here. The red curve is the one where you wait a couple of weeks, and you can see that the number of ICU beds needed very quickly grows and rapidly overflows the ICU. And so that's an absolute disaster. That's what happened in Italy. It's what happened in other places. It happened in New York City. If, on the other hand, you applied exactly the same mitigation, exactly the same stay-at-home order, but you did it a couple of weeks earlier, then what would happen is you'd follow the blue curve. And you can see that if you followed the blue curve, you would still get a lot of cases, and you'd get a lot of people who are very sick, and presumably a lot of people who would be even dying. But you wouldn't overflow the hospital system, and you'd dramatically minimize the number of very sick people. You'd minimize the damage to the healthcare system. You'd manage the number of deaths. And indeed, in fact, the governor did shut down the state. The stay-at-home order was implemented a couple of days after we did these calculations and made them known. Obviously, the governor was contemplating these sorts of stay-at-home orders anyway, and California was the first to do a preemptive stay-at-home order on March the 20th, followed by Illinois on March the 21st. And we indeed followed this trajectory and avoided the overflowing healthcare system. So here you can see, again, from Professor Fagan Umscheider's website, you can see here are the data for one state, and here are the data for another state. And you can see that these are the number of deaths from COVID normalized by population. And you can see that it was very much better to be in the blue state than this orange state. And of course, this one is Illinois. This one is unfortunately what happened in New York City. So that tells you that stay-at-home orders save lives. And here's another example calculation where you look at the cumulative deaths as a function of time on the horizontal axis. The blue curve is what you would estimate would happen if there was no stay-at-home order. This curve along the bottom here is what happened when the shelter-in-place or stay-at-home order was implemented. And you can see what happened was that the doubling time was initially about 2.5 days, that's in blue. Then over here, it rapidly went to about 5 days, 6 days. Then it went to 13 days. This is an example of flattening the curve. And by this point in time, you've saved the number of deaths that you've had is about 10 times less than what would have happened if you hadn't done a shelter-in-place order. So just to summarize then, to beat an exponential, what you have to do is reduce this reproduction number, break the chain of transmission. So instead of everybody infecting 2 people, if they can infect less than 1 people, then eventually the epidemic will die out. And so the strategies for beating epidemics have been known for centuries. Take people who are infected and isolate them so they can't infect other people. Find anybody who they may have already infected, but you're not sure of. Find them by asking them who their contacts are and quarantine those people. Practice good hygiene, social distancing, and wear masks for airborne diseases. And if necessary, and only if necessary, do a stay-at-home order and lock down the population where you can get the cases down very rapidly, a very blunt instrument, get the cases down to a number that's manageable by contact tracing. So this is how epidemics typically proceed. They start off slow, they grow rapidly, they have a peak, then they decay very slowly to a point where they're extinct, but then where there's maybe small outbreaks on top of an essentially extinct epidemic. And epidemics can stop because they run out of people to infect, or it can be because the mitigation measures that the population is practicing really prevent the disease from spreading. Sometimes you might think that you see a peak in a curve like this, and you might think it is herd immunity, but that's not true. It's not herd immunity. You haven't infected everybody. All that's happened is that you've managed, under the mitigation measures that are in place at that time, the stay-at-home order, for example, you've managed to slow down the epidemic and prevent it infecting other people. But if you were to remove those mitigation measures, then more and more people would be infected. So the point about epidemiology is it sounds like it's a mathematics and it's a physical science, but I want to tell you that epidemiology is not rocket science. It's harder. And the reason it's harder is that every time you make a prediction, it's guaranteed to be wrong. And the reason it's guaranteed to be wrong is that when you make a prediction, people will hear that the prediction that you've made, and they will adjust their behavior. So for example, let's suppose that you hear a prediction that the epidemic is growing dangerously in the area where you live. So then you're going to say, oh my goodness, that's terrible. So you go out, get some food, and then you hunker down in your basement and you don't go out for days and days and days. And so what's going to happen then is that the epidemic won't grow, because everybody stayed in their basements and socially distanced. And so the epidemic will in fact not grow out dangerously. It will in fact be self-regulated by the behavior of people. On the other hand, now suppose that happens, and now let's suppose you wait a few weeks, and now you hear that the epidemic is basically extinct where you live, or you hear that there are very excellent public health measures to protect you. So then the government might say, hey, the epidemic's fine, you know, we beat the epidemic, we flattened the curve, we're down to here, so no problem, go out, have indoor dining, go to gyms, go to bars, go and have parties. In fact, this is exactly what happened in England. This curve here is what happened in England, and we got down to here in England, and then the government said, everything is great, you know, guys, you really should go out and support the local restaurants. So in England, they encouraged the population to go out to bars and to restaurants. They said they would pay the bill. If you go out to a restaurant and have a nice dinner, the government will pay 50% of the bill to encourage you to do that. And it's a good thing to do, except that, of course, that immediately then drove more epidemics to happen. And so in the end, that program had to finish, and England is now in a lockdown. So, of course, what should be done is you should be paying restaurants and bars to stay closed so that they don't go broke, but they still are not providing a venue by which infections can grow. So that's one of the ways that governments can support the small businesses. So back to the story then, if you hear the epidemic is hardly present in your area, then you stop social distancing, and then that makes the reproduction number get bigger, and the cycle of infection starts again. And so that's why epidemiology is not rocket science, because the behavioral parts of it guarantee that it's not going to be true. But nevertheless, what it tells you is that you can then try to make predictions and advise public health. So let me tell you then, how does one mathematically model these things? I'm not going to go into very much detail about this, but just say a little bit about it. So early on, we used codes that were developed by another biological physicist, Richard Neher, in Switzerland. But the basic model is a standard one that's found in all textbooks. You have a population, some of whom are susceptible for the disease. Then those people can be exposed, so they can then develop symptoms, and they can then either recover, or they might go into a hospital, or they might go into the ICU unit, or sadly they may even die. And the mathematical models, roughly speaking, tell you the probability to go from being a susceptible person to somebody who then is exposed and becomes infected. And you can write down equations that tell you how a disease will progress in time, not by just guessing what the curve looks like, but by actually modeling the mathematics of that. And the advantage of this kind of modeling is that if you have transmission, modulated by some kind of interventions, then you can predict what the effects of those things are. Now, the calculations that we do are very time-consuming and expensive and need to be done on a supercomputer. So you need to be able to write down what those equations are, which have been known for nearly 100 years. There's a lot of parameters that you need to understand and describe how the disease is transmitted. There's typically about 20 of those parameters that have to be estimated from experimental data. You have to have good data, and we get data from the Illinois Department of Public Health. We have to have a very sophisticated way to estimate the parameters and fit our mathematical models to the data. And I'm not going to go into any details about that, but one knows how to do that using a method called Markov chain Monte Carlo methods, which will in fact go back mathematically to the mathematics that goes behind nuclear reactions and atomic weapons. This method was invented in Los Alamos during the 1940s. We use supercomputers because we simulate millions of scenarios to see what's going to happen, and then we can run our simulations forward in time. So let me just skip through some of these things and just show you some of these simulations. So this is an example of epidemic curves. These are predictions that we made on May the 7th, 2020, predicting the hospital occupancy over a period of time, showing data and how our models fit the data. And these predictions were pretty good. They predicted what's going to happen, and you can see they work reasonably well. But we noticed something very funny happening by the time we got to July the 1st. And what we noticed around about July the 1st was that the experimental data, the hospital occupancy, was starting to deviate from the predictions of our models. Our models were predicting that the epidemic numbers would die away like this, but now you can start to see a little bit of an uptick here. And the other thing that we noticed is that when you look at the people who are getting infected by COVID, previously it had always been that most of the people were elderly people, maybe above 50, 60, 70, or something like this. But what we started to notice was that after about June, the infections were in fact now increasingly from younger and younger people. So we knew that something had changed in the way the epidemic was progressing. And in fact, what happened was the epidemic did start not to go down as we had predicted, but because people were starting to come out and have parties, and the weather was nice, and it was summer and so on, a second wave started, and we could see the turnaround of that second wave. We could see it starting over there. And this uptick was due to the relaxation of the stay-at-home order, the move to different phases of the Illinois opening program, people not social distancing as much. And so by now, here we are at the end of 2020, and you can see that what happened was the epidemic more or less stayed flat, and now we're well into our second wave, which has seems to have peaked already. Hopefully it has peaked. We don't know what's going to happen in the wake of Thanksgiving and and as we come into the holiday period. And of course, everybody is concerned about that. And so this absolutely is not the time to be putting one's guard down. So these are the sort of predictions that we make every week. We make these predictions and we work with the Illinois Department of Public Health and the Governor's Office, along with other other modeling groups in the state, epidemiologists who provide forecasts, kind of like weather forecasts for the state of Illinois. And in fact, there's three university groups and a national laboratory who do these calculations. And I just want to mention that it's very important that we have so many groups. We work independently. And the reason we do this is because in the normal way that science is done, you do some science, you write it up as a paper, you send it to a journal, and it can take a year for that piece of work to get published. Well, that's too long for COVID. We don't have the luxury of waiting for a year. And so we can't do peer review as one would normally do. So what we try to do is get a consensus understanding, some kind of converging description of the epidemic. And if you will, having multiple modeling groups independently working with the public health authorities, it's kind of like getting a second opinion. If you need a serious medical procedure, you will go to another doctor and ask them for a second opinion and make your decision. And so that's essentially how it works with the modeling in the state. One of the things that we've been doing recently with the authorities is trying to estimate whether or not we're going to overflow the hospital capacity or the ICU capacity. And we have a way to do that because what we can do is we can simulate scenarios into the future, look at how many hospital beds are going to be occupied. Here is the threshold, the capacity that you have, and you can estimate how many scenarios are going to overflow those thresholds. And so you can give the authorities some idea of the likelihood of exceeding the hospital capacity. And so that's something that we've been doing, and some of you in the Chicago area may have read about that in the Chicago Tribune last week. So before I go on to what we've been doing at the University of Illinois, the work that we've been doing is available to be read by other scientists or any of you on the preprint archive, medRxiv, and so it's sort of written up and described there. So what I'd like to do is I'd like to talk now about the University of Illinois' rather unique approach to trying to stay open during a global pandemic. So what I'm going to tell you about is what we call SHIELD, and those of you in the Champaign-Urbana area will undoubtedly have heard about this. SHIELD is our program to protect the University of Illinois, and in fact, ultimately will protect the town. It has three groups: target group, the test group, and the tell group. And the way the core of what we do is based around a novel test that we developed here called a saliva test. Normally, you know, if you get a COVID test, you get something stuck up your nose, in some cases really far up. It's rather intrusive. And we developed a test here, not me personally, but Paul Hergenrother, Marty Burke, and others in the chemistry department, and also the Institute for Genomic Biology, developed a test where you just drool into a test tube. And from that saliva, you can then do a PCR test, and it turns out to be extremely cheap, non-intrusive, and we can get the results super fast, within about 5 to 12 hours in most cases. And then what I've been doing is using modeling with other colleagues to figure out who we should be testing and when we should be testing them, how often, and really trying to estimate whether the SHIELD program will work. And as I'm going to tell you, it's not just testing. Testing on its own is useless. It'd be like taking a patient and waving a thermometer over them and hoping to make them better. That's not going to do anything. What you have to do is wave the thermometer over them and then give them medicine if their temperature is elevated. And so we have a whole range of mitigations that we do in order to cut transmission, and I'll get onto those in a minute. And then lastly, we have to tell people the results of their test, and that turns out to be quite non-trivial. And to do that, we work with the Champaign-Urbana Public Health District, and we also use an app that was developed at the University of Illinois, an exposure notification app called the Safe Illinois app. And we also provide individualized healthcare in partnership with the OSF. So those are the three legs of our SHIELD program. So let me just now tell you what is the goal of SHIELD. So let's go back to our exponential curve. So here again is the curve you saw a few minutes ago. maybe half an hour or so ago, we talked about the number of severe cases as a function of the calendar day of the time, the slow start and the rapid rise. And this solid line here is meant to represent the ICU capacity. So if you are in this part of the curve, which I've labeled green here, you have an epidemic that is below the capacity, so it's bounded and the epidemic is contained. Everything is good. Once you get into this phase here where you have the rapid rise and the epidemic numbers are exponentially rising, you've got an out of control epidemic. So the goal of SHIELD is to prevent this exponential growth here, is to stay in this bounded, contained phase here and stay there forever. Even if there's a few extra cases that come around because somebody infected comes into the community, we want to make sure that we will never go on this exponentially out of control trajectory. So that's the goal of SHIELD. Now, the only way that you can contain an epidemic is to make the reproduction number less than 1. Reproduction number means how many people you infect if you are yourself infected. If you infect less than one person, then on average, then the epidemic will start to die away because there aren't enough people being infected as you yourself recover. And so you have to make this R number less than 1. And so the way we reduce the transmission is by social distancing. We tell people stay 6 feet away, all those things that you've all heard, wash your hands and so on and so forth. We also restrict the class size. So if the classes aren't too big, then that means that even if somebody is infectious in the class, there's a limit to how many people they will infect. And similarly, if the class size is small, it makes it more unlikely that you're going to have somebody in the class who is infectious. We have universal masking on campus. So if you're on campus, you have to wear a mask. Then what we do is we test people using the saliva test. And if you test positive, you get isolated. In fact, you can stay isolated at home if you are able to isolate. If you're not able to isolate safely at home, we put you in a hotel so that you can be alone there and not infect other people. And then what the Champaign-Urbana Public Health District does is they ask you who are the other people that you've been around in the last couple of days. Did you go to a party? Did you see your family? Whatever it may be, were you in a class? And then all those people who could have been in contact with you are then asked to quarantine. And we also use the app to tell people that you may have been exposed. And I'll say a little bit about that in a minute if I have time. So the question then you might want to ask is, if we do all those steps, is that guaranteed to make the reproduction number R less than 1? So this is a mathematical question. If it's not going to, if you do all those things and the reproduction number is still greater than 1, you won't make the university safe. And so we have to see, is the university going to be safe? So what we did was we asked the following questions. Who should we test? How often should we test them and when should we test them? What other mitigation strategies can be effective? And can we reopen the university in a hybrid way safely? Hybrid meaning that we do a mixture of online and in-person teaching. And what we discovered is this. First of all, the first thing that we discovered is this. The original conception for how SHIELD would work would not have worked. In other words, we have to test people more frequently than we had expected in order to be able to maintain a safe campus. We discovered that we should test everyone, we should test people when they arrive, and we should test them frequently throughout the semester. And in fact, we test most students twice a week on campus. Some students we test 3 times a week. Some staff and faculty and graduate students, we only test once a week, depending on their risk. And then what we discovered was that all these mitigation steps, there's no one silver bullet, there's many of them, do in fact make the reproduction number less than 1. So let me just tell you a little bit how we try to answer that kind of question mathematically. So if you think about what a university is, it's a bunch of students and faculty who live at home, and then several times a week, they come together in a particular room to have a class. It's kind of like Groundhog Day. every Monday, every Wednesday, every Friday. You go to the same room, hear the same lecture, deliver the same lecture of your professor. It has a timetable. So we simulate that timetable. The students and the staff and the professors, 45,000 of them, going to different zones, lecture rooms, bars, restaurants, dormitories, coffee shops, libraries, other gathering places. And we ask, as they move around, how do epidemics spread? And we work out the social network of the university. And here it is. This is a graph. It's completely incomprehensible, but there it is for you to gaze at in awe, if you will. The nodes in this graph are classes, the edges are the students. And what we discovered was that the university is what's called a small world network. So you've heard of maybe the game 6 degrees of separation, 6 degrees of Kevin Bacon. How many people does it take to get from you to somebody you know to somebody famous like Kevin Bacon or Barack Obama or whoever you want? So what we discovered was that there's not 6 degrees of separation in the university, there's 2.5 degrees of separation. Because people are going to the same classes, they're going to some of the same activities, it's a very closely tight-knit community, which is great, it's nice, but it means it's the ideal case for a disease like COVID to rapidly spread. So why is COVID so dangerous? Well, you've seen some of the statistics before, but the thing that we realized very early on and is still not fully appreciated, I would say, by some of the health authorities, is that the coronavirus is spread by aerosols, not by droplets, but by aerosols. Droplets are sort of big globs that will fall to the ground within about 6 feet of you. But aerosols are even smaller, less than 5 microns or so. And they spread and they can diffuse around in the air and they can be there in a room for much longer than just falling to the ground very quickly. So we know that there's compelling evidence now that, that this is true. COVID can be spread by people with no symptoms. Maybe even as many as a half of the people who spread COVID have no symptoms, don't even know that they are infectious. And in fact, 10% of the people who are infected are the ones who contribute 80% of the transmission. It's not like everybody just infects the same number of people. Most people don't infect anybody at all, but then a few people infect a lot of people. And that's called super spreading. And if I have time, I'll say something about that at the end. So that's why it's so dangerous. So how do we model it? Well, we follow each student as they go to class, go home. We follow them having parties. We have about 7,000 students having parties 3 nights a week. We model the physics of aerosol spread and virus infection in different locations. We model the mitigation steps, what happens when you have classes online, what happens when you wear masks, all of these things. And we try to make the worst case assumptions. So what happens? Well, when students return to campus after summer, that's when we started SHIELD, we predicted what would happen if they came to campus. And what we predicted was something around 300, 200 plus or minus 100 different cases. In fact, we did these calculations many ways, and I'm not going to go into the details here, but we did it by 3 different ways. And we found that somewhere between 200 to 400 students would arrive on campus infecting the community. And in fact, what we discovered was in the entry period, about 288 cases were detected. And by the first day of classes, we had 367 cases already, just from people coming in from their summer holidays. So how does the modeling really help? Well, what it does is it tells you trends. And again, I want to emphasize this. Modeling doesn't tell you the precise numbers. Just as I said before, it's harder than rocket science. Any prediction you make can be falsified by people changing their behavior. So we can't predict the behavior, we can predict the epidemic. So the first thing that we discovered was that suppose you test people and isolate them, and you test them once a week. What we discovered was that would mean that essentially the entire university would get infected. and you'd have 26,000 people in quarantine. That really would not work in protecting the university. If you test on a 3-day cycle, that enormously reduces the number of people who get infected and reduces the peak number of people in quarantine. So just doing that, just testing and isolating and quarantining people already helps. It doesn't eliminate the spreading, but it reduces it a lot. So there's a multi-layer approach to reducing transmission, because what we're trying to do with COVID is it's a race against time. So let me explain to you what happens. We do our test at Illinois. Within about 12 hours, if you're positive, you will get your result back. You'll get it back even quicker if you're negative. The minute we get that test comes off the PCR machine, we have a team that within 30 minutes will contact every student and will tell them that they have been tested positive and need to isolate. And the reason we rush so much is that when we model this, and I'm not going to go through this in great detail here, what we discovered, and other people discovered this too, was that if you wait a day or so to do contact tracing, by then it's too late. Infected people have already infected other people, and so the disease has spread. So it's only by catching people early can you stop the transmission. And you literally have to do it within a day. Otherwise, there's no point in doing it. So you have to get the test results back fast, and you have to do the contact tracing fast. Another thing that we discovered was that we can use apps to tell you if you've been in contact with somebody who's tested positive. And we developed an app that, without violating anybody's privacy, without using GPS or anything like that, can tell you if you have been near somebody else who has tested positive. And again, I'm not going to go through this in detail. I want to get onto other things, but the app is actually probably the most successful COVID-19 app in the world, because it is also used as the delivery mechanism, and it's also used as the way to allow you to access university buildings. Then everybody has this app, and so we have a very high adoption rate of the app, which means that we can tell quite well if you've been near somebody who is positive. So I'm not going to go through the app in detail, but I'll be happy to answer questions about that. So what you end up finding is this. Let's look at this reproduction number and all the different ways that you can try to mitigate an epidemic in our university of 50,000 people or so. This is the reproduction number. High is bad, low is good, and if you don't do anything, the reproduction number is about 3.2 in our calculations. If you test twice a week, that doesn't make it less than 1. If you do twice a week and you also have universal masking, now you're down to about 0.83. If you do small classes, you test twice a week, you wear masks, and you do contact tracing, you can get the numbers down to about a quarter or half, something like that. And that's enough to disrupt transmission. We can also work out where transmission occurs. I'm going to skip through these things. And the other thing that we can work out is how long it takes for epidemic to relax away out of the population. Now, I showed you that at the beginning of this semester, about 300 people came into the university. You might say those people who are infecting other people, how long does it take for those infections to die away? And what we estimated was that it would take about a month for that to happen. And the reason it takes about a month is the smaller the reproduction number, how much less than 1 it is, the faster is the decay rate. And we estimate that R is about a half, something like that, for our campus. And I'm not going to go through this in detail. The factors that contribute to this decay turn out to be things like whether people are complying with testing, whether people are complying with isolation, whether people are holding lots of parties and things like this or not. So there's a lot of different factors that go into this. Okay, so let me show you how this worked. So what have we learned from doing nearly 1 million tests on the University of Illinois campus since July? So that's really 1 million tests. We do about 10,000 tests a day. On any given day, we're doing about 1% of the tests in the United States. Now, the way we keep track of things, the way we keep score, is what's called a case positivity, which is the number of new cases over the number of tests that we've done that day. And so what does it tell you? This number, you may not be familiar with it, so let me just explain how it works. If you turn it upside down, you look at it the one over that number, it tells you how many tests you have to do to find a new case. In other words, if I just go around randomly and test people, how many people do I have to test before I find somebody that's infected? If your positivity is 1%, that's great. That means you have to do 100 tests to find one new infected person. If, on the other hand, your positivity is 25%, as it was at some of the other universities in the state of Illinois during early September, that means that you only need to do 4 tests to find a new infected person. In other words, there's lots of infected people around. And so that's why this number is so important. So here's what happened at the beginning of the semester here. So this is the students returning to campus. You can see a spike in the number of cases just before the first day of classes. The orange curve here is this case positivity, and this 7-day average of the case positivity at the time that this graph was made at the beginning of September was about 0.73%. That's the situation on September the 10th. Here we are a month later, and so here's what you can see has happened. First of all, by then we've done nearly 600,000 tests. And our positivity, our 7-day average positivity is 0.14%. Actually, it got down to even lower than that. So what that means is, in order to find a new infected person on campus, we had to do 700 tests to find somebody. So we really had the epidemic under control. What you can see happening here is the number of cases went up. On this one day, we had a little over 200 cases, 220 or something like this. And then the number of cases fell, goes down like this. This number here was higher than we had expected. And the university stayed open, but we instituted a essential activities only order. You can see what happened was that the SHIELD program reduced the number of cases, and the positivity, the grounding, as the students referred to it, kicked in sometime around September the 3rd. It lasted for about 2 weeks. The positivity went down very low. And then after it was relaxed, the positivity went up slightly and then fell, and reaching eventually this number around about the middle of October. By comparison, at that time, Champaign County's positivity was nearly 10 times as much. The region's was 10 times greater than that, and the state's was about 5%. I think these numbers are right for this particular date. So the time scale it took for these numbers to get down to here was indeed about a month. So let's take a look at the last day of instruction. So now you can see how the whole semester worked. We had arrival screening, we had parties and non-compliance at the beginning of the semester. We had essential activities order. Regular activities resumed about September the 16th, a slight increase here. The cases decay to its low point around the middle of October. Round about here, we started to have football season, we had Halloween, we had an election. So the cases started to rise again in the region and also in the university. And then by the last day of in-person class, we were down at about 0.32, having gone briefly above 0.5 on these days here. And so you can see that the SHIELD program has really ameliorated the epidemic and prevented any kind of exponential rise. So we had no exponential growth, and I'll show you in a minute, even though at this time, the number of cases in the region was growing exponentially. We had no serious illnesses, no hospitalization, and no spread to the community. And the university stayed open. And that meant we could give our students the educational experience, not quite the one that they would have had normally, but at least many things were much better done with this way than if we had been a fully remote campus. And so this was really proud of that. Since then, we've had a spike due to Halloween. So the cases jumped up after, not Halloween, excuse me, after Thanksgiving. And so currently the situation is shown here, where now 900,000 tests, positivity of 0.52, 6.5 in Champaign if you exclude us at the University of Illinois. Again, in Region 6, if you exclude us, it's about 11%, and in the state, it's about 10%. So basically, the town and the county and the region, as you go outwards from the university, you can see that that the number of cases goes up. By protecting the university, we've also helped protect our region. And you can see this here. So in this graph here, what you're seeing is in blue is the number of cases in Champaign County, excluding University of Illinois. In the orange, you're seeing the University of Illinois. This is just a regular scale. This is that logarithmic scale I showed you before, and the exponential growth is a straight line on this graph. So what's happened since October is the number of cases in the neighborhood, in the region, have been growing exponentially. And we know this because the governor has talked about that, and currently the whole state is in tier 3 mitigation. On the other hand, the University of Illinois has, the number of cases has stayed flat. All right, so I think I'm going to end there. So I think that we've gone on long enough. I'm going to skip this, but I'll be happy to take questions. And let me just skip to my last slides. So what I've shown you is that exponential growth is something that's really hard to stop. But here at the University of Illinois, we developed a high frequency, high throughput testing of everybody, which gives a very clear picture of the epidemic and stops transmission. There's no one thing that stops the transmission. Multiple things will do it. And what I didn't tell you about, but we can get into in questions if you like, is how transmission can occur through super spreader events. One person can literally infect hundreds of others, and that's why we have these rules about the size of gatherings in Illinois at the moment in order to prevent these super spreader events. So with that, I'll stop, and I'll be happy to take your questions.
Thank you. As you can imagine, there are lots of questions, and many of them focus on comparing the data that you've collected at the University of Illinois with other places. One question asks, have you compared the U of I to other US universities, including Michigan or other large universities?
Yes, we have. You know, most universities have not been able to had the resources, or were able to do what we have done. There's a few that have. Cornell is one example where I, for example, talk a lot with my counterpart at Cornell, and we swap notes there. University of Illinois has had a lot of cases because we see the whole iceberg, we see everything, whereas in most other places where they do not have this high frequency testing of everybody, they only see the tip of the iceberg, they only see a few of the cases. So we have, probably other places have as many cases as we do, but they just don't know it. And I can give you an example of ISU. Most of the universities had this burst of cases right at the beginning. Let me show you where it was over here. This burst at in this weekend around August the 31st, that happened at the University of Illinois, it happened at Cornell, it happened at ISU, it happened at many places. Students came back, they parted and so on, and in fact at Cornell they also had an essential activities order for I think same time as we did, two weeks, in order to sort of cool things down as well. But our peak positivity went on one day, the highest we ever got was 2.8%. At Illinois State University, which didn't have the advantage of this sort of program, their positivity was a factor of 10 times higher than that. And that meant that they had an out of control epidemic there. So yes, this type of operation makes possible a mode of behavior, a mode of teaching, a mode of university experience that's not really possible in any other place. At other universities, several others did similar things to us. Duke University had a very good program. Boston University, Cornell. So some of the different universities have differences. For example, at Cornell, they are in Ithaca. They're 4.5 hours from New York. It's a much more isolated community than here, where we have many students go back and forth, say from Chicago or other areas. Because we're nearer, and so that brings cases into the university, and we've seen that from the reports of contact tracing and so on. So there are differences in terms of the performance, but basically the same trends you've seen across every university that I know of, which has done something similar to what we've done.
Thank you. There are several questions that around the theme of replicating the U of I approach and making the saliva test generally available. I know there's new information available about that as of today, but there are also concerns about FDA approval. So could you talk a little about that, please?
Sure. So as I think the Chancellor mentioned and was reported in the newspaper yesterday, we are working on a plan to be able to produce the saliva test and make it available to the Champaign-Urbana community, and it's a very non-trivial problem to do that. There's a lot of, it's not just doing the test. You have to be certified to be able to do the test, so you have to have facilities to do it. We have the extra facilities, and they're going through certification at the moment. We also have to have a means to, have people in our IT system. We have a very sophisticated IT system to be able to get people into the system, be able to do that in a way that is compliant with HIPAA and in the case of students, FERPA and other requirements. So those are some of the obstacles. We have to find who are the, have community partners, organizations and communities within the town to work with. And so we've started doing that, and you'll be hearing more announcements about that in the next couple of weeks. But we're working as fast as we possibly can to do these things, and we've had a very good partnership with the cities, with Urbana legislators, governors, the mayors, Champaign, so on and so forth. Some of our partners in the community. So we're really excited to be able to work with the town and hope to be able to show that we can protect a reasonably large town and make that a model for what we could be doing as a nation.
Great, thank you. I know it's a common question for us. We get that question quite frequently. There are a couple of people who are asking about whether you're able to model what happens when or if the COVID virus mutates. And can these models differentiate between the kinds of behavior changes and effects of the mutation?
No, we can't. Our models don't really go down to that level of biology, and our models, I want to emphasize that the models have a sort of window of predictability, but I don't think that you can say, if we make a prediction about what's going to happen in January, for sure it's going to happen, because the virus can mutate. The governor of the state might have a lockdown, or people may decide that they have pandemic fatigue and they just decide we're going to have parties anyway. So all of these things are unknowns that cannot be included in the sort of modeling we do. So it's better than just fitting a straight line, but it's not possible to do the sort of modeling that you could do in physical systems.
Terrific, thank you. We have a question that asks if you could talk a little about the communication plan that led to the success of this modeling and strategy.
So the communication plan, by which you mean the way we work with the students in our community?
Yes.
Yes, yes. So this is a really important thing, and I didn't have time to really spend enough time on that. So the model that we have, it's not necessarily a model that suits a community, but it's a model that works for a university, is this. If you want to enter a university building, you need to be able to show that you are compliant with testing and to show that you have tested negative. And so what you have to do is that you literally, as you go into a building, you show your phone and you show a screen on the app. I'm not going to try to find mine right now, and that says building access granted or building access denied. And so, without having to reveal any health information, the wellness ambassadors who sit at the entrance of every building can tell you, yes, you're allowed into the building, and they can monitor that. So that's part of the communication. That's part of what the app does. But there's more important things. We have to work with our students to let them know why we are doing this, why people get isolated, why we ask people to quarantine. We have to deal with the situation where people say, we don't want to comply with these requirements. We don't want to not have parties. I don't want to not see my friends and so on. And so those have been issues that we've had that we didn't, to some extent, anticipate, and we've had to work very hard to communicate with the students about that. And some of our best partners are the students, in fact. So we work with student organizations. We have a wonderful student affairs group as part of SHIELD, and they work closely with the students to give them information, and to also try to organize safe social events for them, so that people can have some kind of social life, but in a safe way. So we really tried, we understood that students want this, and it's quite natural. And so we've tried to come up with many ways that I didn't have time to talk about, of how to reach out to the students, work with them in a partnership. And by and large, the students have been really fantastic in cooperating and doing these things. So did I answer the question?
I think that was exactly what the question was asking, because it is a big operation to try to manage.
It's a huge operation. There's well over 100 people involved in SHIELD. The leaders of the different parts of it. Every morning we have a meeting at 8:30, a stand-up meeting. There's 20-something people in the room just to go over every part of our logistics. And we haven't talked about where do we collect the specimens. You have these tents, and now we have indoor sites where we have to have people who literally every hour go on golf carts and go from the specimen collection tents to the lab where the PCR tests are done. We have teams of people working late at night doing these PCR tests to get the results out to people quickly. I mean, it's absolutely amazing what happens behind the scenes, and you should get somebody to talk about that to OLLI. It's really quite fantastic how this is done, and that's one of the reasons why what we've done at Illinois has not really been done in the same way at any other institution.
So we have one question that looks at the mitigation effects and whether they might be as effective as a vaccine in a different way. There was news that masks will still be required post-vaccination, even for those who've been vaccinated. So how will mitigation play into a post-vaccine world?
That's a good question, and I don't really know the answer. We don't really know what the vaccine does. So when the vaccine is approved, those FDA tests basically tell you that the vaccine reduces the symptoms of the illness. That's essentially what we know about it. We have no way to know whether it is stopping transmission or reducing transmission. So you may be, if you're vaccinating people, those people who've been vaccinated may still be transmitting the illness to people who've not been vaccinated. We don't know. So, just because that vaccination is going to be starting soon does not mean that you can throw away your mask quite yet.
I'll hang on to mine. We have several questions asking to hear more about super spreader events, I think especially as we go into the holiday season and some of these stories
Yeah,
have been dramatic.
I'd be happy to talk about that. And if you don't mind me spending a few minutes doing that, I think it's really quite important. Let me just flip to my slides on that. So the basic take-home message is one infected person can single-handedly start an epidemic. And you might say that sounds a bit far-fetched, but it's actually happened. So let me just tell you this, and this won't take very long. When we talk about a super spreader, we could mean a person, or we could mean an event, or we could mean an environment. And the whole idea of a super spreader is it's one of these things that starts off multiple chains of infection. So let me give you an example. And here's an example from Chicago. So this was from the CDC weekly journal. It's called Morbidity and Mortality Weekly Report. So here is an example of something that happened in Chicago in March. Actually, I think it was March. One person attended a funeral in Chicago, and that led to a whole bunch of people being infected and 3 people dying. Just that one person going to a funeral. So here's another example. This is somebody riding on a bus. One person on that bus was infected, and they didn't know it, and she infected a third of the people on the bus. Okay, and in fact, you might say, well, maybe she infected only the people who are within 6 feet of her. But as I told you, we believe that COVID is spread predominantly by aerosols, not by droplets, not by touch or things like this that we thought initially. So everybody in the bus, no matter how far apart they were from the infected person, got infected. As far as I remember, the only person who didn't get infected was the person who was sitting by an open window. Okay, so ventilation is critically important. And this is a story that's really quite a sad one. This was a rural wedding, and this happened at the end of August. And I know that this has happened in Champaign as well. I know that the people who have had weddings, large events, and in violation of public health ordinances and against state regulations, and those things are not harmless. So here is an example. This was a wedding that was held in a hotel, a restaurant of a hotel in Maine. There were more people there than the 50-person limit. They weren't wearing masks. They weren't socially distancing. Next day, some people noticed that they had symptoms, and one person infected 147 other people, and that led to at least 3 deaths. That was August the 30th. Okay, so that's one person infecting everybody at the wedding, and those people at the wedding who got infected other people. So that story is true as it was known at September the 10th. Okay. So here's a headline. This is now September the 15th. Now you've got 7 people who've died from this event. 7 people who died. They didn't even attend the wedding, but they were infected by people who did attend the wedding. And the number of cases has gone up to 176. Well, then you might think 7 is bad enough, but by this date, September the 21, now we've got 8. The 8th person has died, and 270 people were infected by COVID. Okay, just by this one event, which was in violation of the local statutes. So the point is that what was so bad about these kind of events? Well, as you know, as I've told you, you have aerosol transmission. So these small droplets are going to spread if you are indoors, so they can't be blown away. So you need poor airflow. You need to be there around people for a long period of time. It's not the idea that you're 6 feet away and then you're fine. And if you're in contact with somebody for several hours and people are talking loudly, so they're emitting lots of aerosols, and in fact, if you're talking loudly at a party, you're emitting the virus maybe 30 or 50 times as much as if you were just standing there, not even talking. And half the people who transmit infections don't even have symptoms. So you never know. And so these types of events are very dangerous. That's why whenever you read in the newspaper about the jurisdiction worried about cases, and so the first thing you do is close down indoor dining, close down bars, try to limit gatherings to small gatherings, no parties. The reason is because the worst case scenario and the best case scenario for COVID spreading is you're in a bar, you're talking loudly because there's loud music, you're not wearing a mask because you're drinking a beer or something like this, and you're there for a long period of time. And so it can be a very dangerous environment. And one of the things that we've been fortunate about in Champaign-Urbana, we use the app in order to restrict access to buildings. We've partnered with some of the campus town bars and restaurants, and they also use the app to restrict access, so that with the intention of trying to get people who are enjoying the facilities of the restaurant or the bar, that the people in there are, as best as you can tell, COVID free. So I think that's really all I want to say about super spreaders, which is basically, please really follow these rules. When the CDC or IDPH or CUPHD says, please don't travel during Thanksgiving or Christmas, please try to restrict parties, try not to mix households, really meet outside if you have to, really try to do this. We're in a situation where we've passed the peak of this second wave in Illinois, but it can very easily go up. And you saw in the university that even at University of Illinois, we saw a spike following Thanksgiving. And I'm sure you're going to be reading a lot more about those spikes in the newspapers nationwide.
Well, this has been, we're right at 5:30. There are more questions than could ever be answered in the course of a regular presentation. I do want to let everybody know we have been recording this, and we will send the link to this lecture. Several people have said, can I get a copy of the slides so I can go back and look? But we will send, tomorrow I'll send everybody who was registered the link so people can revisit this.
No, I'll be happy to send you, Chris, a copy of the slides, and if you want to make them available to the OLLI participants, I'd be happy to.
That is so generous of you. Thank you so much. I'd like to thank you again for doing this. Thank our friends from around the state for joining us. It's been our biggest statewide audience for an event. And Nigel, thank you so much.
Well, thank you for your interest. I'm happy to do it, and I hope everybody found this interesting. That's why I went on a little bit longer than I expected. I hope you all learned something and stay safe.
Thank you. I'm keeping my masks at hand. Thank you very much. Well, stay safe. Have a lovely evening.
Thank you all.
Everybody. Great to see you all.
Bye, everyone.
Bye. Thanks.